This time, we need to identify whether the given matrices here under the linear transformation would be an onto or a one-to-one linear transformation. And after that, we're also going to insert the idea of isomorphism, since once we're able to identify that our transformation is a one-to-one and onto, it is automatically an isomorphism. But before that, let us try to review how do we solve for a one-to-one linear transformation here. The transformation is a one-to-one transformation if we could show that the kernel of T contains the zero vector alone. So if we could show that, then definitely we can say that the linear transformation defined by these two matrices is a one-to-one linear transformation. As for the onto, we need to show that the dimension of your domain is equal to the dimension of the basis of your range. If we could show this, then automatically we can say that our linear transformation is also an onto. And with that two conditions met, we can show the isomorphism. Before we start showing these two, we have to understand what type of zero vector we're looking for and what is the domain. This could be declared by our matrix here. Since both of them are a 2 by 2 matrix, there is also a 2 by 2 matrix, which is represented by m by n. That form or the type of linear transformation these two matrices exhibit is the transformation of r to the n to r to the m. In short, the linear transformation here is r2, which is our n, to r2. Okay, this is the definition or the description of the linear transformation involving these two matrices here. And what is again the purpose of these two? We can actually determine here the domain R2 as mentioned here. So our dimension of domain is the dimension of R2. Let's insert it later once we discuss the onto. But of course, it's very obvious here for some of us who are able to identify the dimension just by the given of this linear transformation. And the kernel of T is equal to the zero vector. It is related to our codomain here. This should be the set where we are going to refer our zero vector. That would mean the zero vector is an element of R2. In short, it's this, the zero vector is this form, 0, 0. Okay? That's why this is very important, and this should be the initial step in showing whether linear transformation is a one-to-one and onto at the same time. So let's try to continue with our process here, or we start with our process in using this first matrix, as we are going to show whether this is a one-to-one linear transformation or an onto linear transformation. Let's have this first. The transformation of vector v is equal to the product of matrix A and V, which is equal to the zero vector. This is how we show first the kernel of T being equal to the set containing zero vector. Of course, our zero vector is already given here. But what about our vector V? This should be the element of our domain. So that would mean our vector V, okay, is also in R2, comprising v sub 1 and v sub 2. And we are going to solve for these components that will satisfy this equation. And if would be the zero vector itself, then we are going to have the kernel being 0. So first, let's come up with the reduced row echelon form of this. That's the first step we need to do, the reduced row echelon form of our matrix. We are going to have here 2, 0, 0, and 3. We're going to multiply, not equal. We're going to multiply 1/2 to row 1. Why do we use the reduced row echelon form, even if we can automatically establish here the, or if we're going to multiply this with v sub 1, v sub 2, of course we can already multiply 2 times that and 3 times this, equate to the 0, so we can automatically solve v sub 1 and v sub 2. But why do we still use the reduced row echelon form? Aside from number 1, of course, we need to practice that, so that if we are going to have a different form of matrix, then it will be easier for us to do that. But at the same time, the reduced row echelon form could also be beneficial in determining the onto linear transformation. So again, let's just do that. And we're also going to multiply 1/3 to row 2. By the way, this is row 1, row 2. So this would mean we have 1, 0, 0, and 1. This is now our reduced row echelon form for our matrix A. So the first thing here is, going back to this, we have 1, 0, 0, 1. We're going to multiply our vector v, v sub 1, v sub 2, must equate to our 0 vector on R2. Okay. By multiplying that, we will get v sub 1 equal to 0 and v sub 2 equal to 0 as well. In short, the vector that satisfies the equation is the 0 vector in R2 as well. With this, our kernel of T is a set containing said vector. And since our kernel of T contains the 0 vector in R2 alone, we can say that this is a 1-to-1 linear transformation. So we have now established the first condition for isomorphism, by the way. 1-to-1 linear transformation. Okay. Now, how about for onto? We are going to use the same reduced row echelon form 1, 0, 0, and 1. Why? Because when we go back to determining the onto linear transformation, we have this condition here. The dimension of the domain must be equal to the dimension of our range. This is our domain. Okay? The dimension of domain is just equal to the space itself. Since it's in R2, the dimension of our domain is equal to 2. With this, we need to show that the dimension of range is also equal to 2, so that we can say that this linear transformation defined by this first matrix is an onto linear transformation. We can do that since we're talking about range. The range is equal to the column space of A. Column space of A means, looking at our columns here, how many columns contain leading ones. After our reduced row echelon form, we have 2. Okay, so our basis for the range of T is equal to the column space of A, meaning our original matrix here, 2, 0, 0, 3. That contains here 2, 0, and then 0, 3. With this, our basis for our range, the dimension of the range talks about the number of elements that can be found on the basis of range is equal to 2. With this, and the already established dimension of domain being equal to 2, we have here the dimension of your domain is just equal to the dimension of the basis of your range, which is 2 equal to 2. With this, we have now established that our linear transformation of the same matrix is an onto linear transformation. Okay? So this is how we show one-to-one and onto linear transformations. But of course, with these two ideas, one-to-one and onto, let's just insert the idea of isomorphism. This is only established if both are satisfied, one-to-one and onto linear transformation. Okay? So let's continue with the second. Again, the point here is to solve first whether it's a one-to-one. So we are going to make sure that the kernel is equal to 0 vector, which is still an R2 because this is a 2x2 matrix. And this is still using the same definition of our linear transformation, R2 to R2. So we're going to establish this as well. Is equal to A times vector V is equal to the 0 vector in R2. But first, the reduced row echelon form of this, we have 1, 1/4, 0, and 1. We just need to make this 0 to make this a reduced row echelon form. So negative 1/4 of row 2 plus row 1 for a new row 1. We have here 1, 0, 1 here as well. So your negative 1/4 times 1 is negative 1/4 plus 1/4 is 0. So you could automatically predict here because we have the same reduced row echelon form of the first matrix. But nevertheless, let's just continue expressing it like this. So we're going to have satisfy this form, multiply with our vector in R2 and equate to the 0 vector in R2 as well. We can say that v sub 1 is 0, v sub 2 is 0 as well. Hence, the vector comprises the 0 vector in R2. And with this, the kernel of T is a set containing 0, and 0. In short, the second matrix also shows a one-to-one linear transformation. Okay? For the basis, because we still have the same domain. Now, we have the same domain. Okay? The basis will again use the same reduced for echelon form, 1, 0, 0, and 1. Okay? So with this, we have two columns with leading 1. So the basis for the range of T of the second matrix, we'll have this 1, 0, 1/4, and 1. So you have here 1, 0, 1/4, and 1. By the way, why do I keep on repeating this process where I can automatically declare that the dimension of range is 2? It's because we also need to really review how do we express the basis, how we show the kernel. So it would be a hitting many birds with one stone. So the domain here, the dimension of the basis of your range is equal to 2. As this is equal to, again, the dimension of our domain earlier. Dimension of our domain is equal to the dimension of the basis of the range. 2 equal to 2. This is also an onto linear transformation. We have a one-to-one. We have onto. In short, this is also an isomorphism. Okay. So this is how we show how do we determine one-to-one and onto linear transformations. At the same time, the inserting of the idea of isomorphism for these two given 2x2 matrices. Thank you very much for watching.